Hello, and welcome to our TI Technology webinar hosted by Texas Instruments Australia. We are excited to bring you Vector Calculus, Unit 3, Topic 4 from the QCE Specialist Mathematics course with a very experienced mathematics teacher and lecturer and TI Technology user, Mr. Peter Flynn. My name is John Bayman, and I am your host for this event. I teach mathematics to Year 7 to 12 students at Lachlan Catholic College in Darwin, where I use TI technology to help students make stronger connections in their understanding of the mathematics. And more importantly, I'm excited to introduce our panelist for today, Mr. Peter Flynn. Hello, Peter.
Good evening, John.
Good evening. Peter has been a mathematics education teacher and lecturer for over 30 years in a variety of educational contexts. He has a rich knowledge of computer algebraic systems, CAS for short, as well as various examination boards. He is also co-author of our recent QCE Mathematics Methods Teacher Resource Booklet, which I would highly recommend that you can download or get from the TI website, as well as the newly released Specialist Mathematics TRB.
Thanks very much, John. Good evening, all. So it's a little bit wider than vector calculus this evening. We'll have a look at some vectors as well. So my name's Peter, obviously, and there's my email address if you wanted to contact me. The outline for this evening, try and get through 5 sort of areas. First of all, look at Cartesian equations of curves, and then look at 2 intersecting lines where they meet. Look at using the cross product to calculate the area of a triangle, and we'll illustrate that through the use of the notes page or notes application. We'll have a look at determining whether 2 particles collide or not, given their position vectors as a function of time. And the final example, we'll have a look at some basic vector calculus. So that's the outline or the plan of attack for this evening. The first example, this is in a notes page. We're going to look at a Cartesian equation of a curve. And the example there is find the Cartesian equation for the curve represented by that vector equation, where t is a parameter that belongs to the reals, and we're asked to state the domain and range of the Cartesian relation. So first point is we're in a notes page, so you can write some text. So I've got some text here. On the handheld, if you press Control menu and then go to number 5, format text, up comes a format text dialog box, and you can alter the appearance of your text. So currently it's in TI-Nspire Sans. It's 11-point size font. And the way to move through a dialog box is by pressing tab. So if you wanted to bold it, you would click on that, italics on that, if you wanted it underlined on that, etc., etc. So that's basically giving you a little indication on the handheld how to produce text the way you want it to look on a notes page. It's far easier using the computer software, as you can see up here. So we'll press escape, and I use the Microsoft Word snipping tool, and I've snipped this example from the Specialist Maths Teacher Resource book that John mentioned at the start of the webinar, and so I've just pasted it in. So far you can see for the notes application that you can write text and you can also paste images into that application. You can also do some mathematics, and we'll see that in a later example. So what we have here is we have a graphs page, and we have the parametric equations from the vector equation. So x is equal to cos squared t and y is equal to sine squared t. So how did we produce this particular page? Okay, so it's a graphs page, and what you would do is, first of all, we press menu and we go to number 3, graph entry edit, and what comes up is a list of possible ways that we can graph, or graphing modes. And one of them is number 4, which is parametric. So if I press number 4, I already have x1 of t and y1 of t. They are already added into the entry line. That's why in this example, it's starting at x2 of t and y2 of t. but all I need to do is with the navigation pad is just press up. And what I've done there is you can see that I've entered x1 of t to be cos squared t. Notice that it's written a little differently to the way we write it in mathematics. And y1 of t is sine squared t. Because we've just got an argument there of t, it's quite sensible to have t going between 0 and the numerical approximation for 2 pi. And I've used a t step there of 0.13. That ends up, it's actually a multiple of pi. And so you enter those and press enter, and you end up with a Cartesian equation. It looks suspiciously like y equals 1 minus x. But what we would do, I think, you can do this one of two ways, actually. You can do it graphically and then confirm it algebraically, or do it the other way around. There's no real one way being better than the other. So on a notes page here, this is again a snip from the Specialist Maths TRB, Teacher Resource Book, where we outline the solution. So we let xy be any point on that curve that's defined by r of t being the vector equation. The parametric equations are specified as we've already mentioned. And what we do is we exploit the Pythagorean identity by saying, well, okay, if y equals sine squared t, then we can write that as 1 minus cos squared t, and we know that x is cos squared t, so we can make that substitution. So we can quickly glean that the Cartesian equation that corresponds to this vector equation is y equals 1 minus x. And we can also have a nice brief study of the domain. So, for example, cos t lies between -1 and 1. So therefore, when you square cos t to form cos squared t, it's always going to be non-negative. So cos squared t is going to lie between 0 and 1. And so that's indicating that the domain of our Cartesian equation is from 0 to 1. And we can see that from our plot there. And similar analysis shows us that the range will also be from 0 to 1, because sine squared t lies between 0 and 1. You could also, to augment this, tease it out a little bit further. On the next page, what I've done in function graphing is I have plotted the graphs of cos squared x and sine squared x, and also graphed the horizontal line y equals 1, and it just shows that the both those curves satisfy both that inequality there and that inequality there. A couple of points that you may glean from this page is the labels for cos squared x and sine squared x, f1 of x and f2 of x respectively, is different here to the label that we have for that horizontal line, y equals 1. By clicking on that line and either pressing a control menu on the handheld or right click on the computer, you can go to a command called attributes number 3, and you can choose a different line weight. You can, just arrowing down, choose a line style, and I've chosen dashed. But you can also choose a label style. And so I've chosen that label style y equals. In this, you're always got an arrow which gives you a cue as to whether to press left or right with regards to seeing what sort of selections you've got. So if I press on that, I could have had that as y equals f3 of x, f3 of x equals 1, etc., etc. So if you wanted to have your labels set a little bit differently to the traditional way that we see in the entry line, then that's the way to do it. So I'll just press escape there. And the other thing you may note is that you can also set your window. In this instance, we're talking about trig functions, so it's a good idea to have your endpoints for the viewing window along the horizontal axis there to be in terms of pi. So I've got there -2 pi to 2 pi, and we've got a scale there, or each tick mark is worth pi on 4. Now, another quick way that you can set a window is these values can be edited. So I make contact with -2 pi and click once and click again, and it opens up, so it can be edited. So I could change that to anything I like. While we can edit in there, if I press tab, nothing seems to happen. But if I press tab again, 2.5 can now be edited. I press tab and tab again, and 2 pi can be edited. Press tab and tab again, and -1 can be edited. So rather than going through the menu and window zoom, you can actually set windows on the screen just by opening up one value and then just pressing tab. What tab does is a bit like the function that tab has on pages on the web, where it takes you to an active part of the screen. So that's what's going on there. So these are active parts of the screen, and they can be edited. Okay, so I'll press escape there. And that completed our first example. Just a reminder that there are other Cartesian equations that students need to be aware of. And the Cartesian equation of a path given as a vector equation in 2 dimensions, well, we've seen the simplest example, which is a straight line, but you can also have circles, and that's the Cartesian equation of a circle. We also have there an ellipse, and that's the Cartesian equation of an ellipse, and also a hyperbola, and you've got 2 forms there for the equation of a hyperbola. And so what we'll show this evening, the principles are the same, whether you've got a line, a circle, an ellipse, or a hyperbola. So our next example is a try this, and we'll build in a little bit more information here. This now we link to the position vector as a function of time. So the parameter t is now representing time. And we're asked to find the Cartesian equation of the path of a particle which moves with that position vector at time t, and t is obviously greater than or equal to 0. And the 2 parts there, this comes from the Specialist Maths TRB again. Part A is plot the path of the particle, and part B is describe the motion of the body. So again, the Microsoft snipping tool has been used to paste this example into a notes page. So it gives you an indication that when you do your teaching, conduct your teaching and do some worked examples with the students, you can perform these worked examples all within the TI-Nspire environment, which is very handy, rather than moving from TI-Nspire to PowerPoint, even to the whiteboard, etc., etc. Okay. Now I've already taken the liberty to plot these, and so again, just as a reminder, plotting those parametric equations, which gives us the path of the particle. We press menu, graph entry, edit, number 4 for parametric, and then up with the navigation pad. And you can see there that x1 of t is 1 minus 2 cos t, and y1 of t is 3 sin t. Because our argument is t, it's not 2t, 3t, then again, what I've done is I've chosen t values between 0 and that's the numerical equivalent of 2 pi. So this can be edited. I don't need to edit this. I have changed t-step this time. In the previous example, it was 0.13. I've divided that essentially by 4, although you can't see it because of the number of digits that are displaying. But t-step here is 0.032. I've made it small. Sometimes you can make the t-step too big, and then when you plot the path of the particle, sometimes the path, it doesn't join up to make a continuous curve. There's a small discontinuity somewhere. So bear that in mind when you're choosing your t-step. Okay, so press escape there. You've also noticed here, I'm going to make a couple of comments about the viewing window. The standard viewing window is from -10 to 10 and essentially a -20/3 to 20/3. What I've done here is I've cut it down by 3/4. So we've got a 3/4 sized standard window here. So we'll perform an animation to see how the particle moves when it traverses this path, and then we'll show you how to set up the window using a command called zoom trig, but we'll just leave that to the end. So let's build some excitement into this, and we'll press menu, and we will go to number 5, trace, and then number 4 for path plot, and we'll go to number 4, path setup. And what we want to do now is this is the path setup dialog box. So our graph type, we want to change that to parametric. And the path step at the moment is the same as the T step on the entry line that I showed you just a moment ago. So that's 0.032. That's a little bit slow, and we want the path to develop a little bit more quickly than that. So what we'll do, in a sense, is we'll multiply this by 3, and what that will do is it'll increase the speed in which the path is developed by a factor of 3. We could, if we wanted to, show the future path, and that would, if you wanted to do that, what you would do is just check that box. So that's just a matter of clicking on the center of the navigation pad. And we do want to show the point coordinates because we would like to see the coordinates of where the particle starts. And we might also glean some further information about the coordinates in relation to the trajectory of the curve as well. So I'm happy with that setting. So we press tab all the way through to OK and press enter. And we've now set up our path plot. Now we want to enact it. So we press menu and then trace path plot, and then number 2 for parametric. And what comes up is an animation figure there with buttons, and we can start the animation and we can reset the animation. Notice that we've got the initial t values t = 0, so the particle is starting at -1, 0, and of course we can glean this by putting t = 0 into here, and we get 1 - 2, which is -1. T = 0 into here, and we get 0. So make sure you still remain the bridge between the mathematics and the demonstration. So make sure that the students understand the link between the initial point and why it's -1, 0 from these parametric equations. So, and the other thing is up the top left-hand corner, whenever we're in something, so we're in path plot, if you run your cursor over it, it tells you what you're in and it gives you some advice from how to use it. So you can read that at another time. Okay, so what we'll do now is we'll make contact with the start button and we'll start the animation. And so what we see is that it's moving in a clockwise direction. It's moving in an elliptical trajectory. And hopefully what we've set it up to do is to start at -1, 0 and for 1 revolution to finish at -1, 0. So by looking at and studying that animation, we can now just press escape twice, and that gets rid of the animation buttons and also the path plot. And if we go to the next page, this is a notes page, and this is the solution. It's been snipped using the Microsoft snipping tool from the Queensland Specialist Maths TRB. So what did the animation show us? Well, it showed us that the particle starts at -1, 0. It travels in a clockwise elliptical path with a period of, corrected 2 decimal places, 6.28. So it's got a period of 2 pi. And we can get that from our parametric equations, which are in terms of cos t and sine t. They're not cos 2t, sine 2t, etc., etc. The particle finishes its motion at -1, 0. And you can then go through with the students the mathematical derivation from the parametric equations through to the Cartesian equation of the particle's path. We know that it's an ellipse, but we haven't actually derived its equation yet. And so what we do is we specify the parametric equations and we label them equations 1 and 2. Then from 1, we rearrange 1 to make cos t the subject. And from 2, we make sine t the subject. And then what we do is we exploit the Pythagorean identity, because we know that cos squared t plus sine squared t is equal to 1. So if we square and add both sides, or square and add the two equations above, what we end up with is x minus 1 all squared on 4 plus y squared on 9 equals 1. The 1 comes from cos squared t plus sine squared t. And this comes from x minus 1 on -2 all squared. And y squared on 9 comes from y on 3 all squared. So we can confirm mathematically that the path of the particle is an ellipse with centre 1, 0 and domain from -1 to 3. And that makes good sense there with that tick mark there of 1, -1, 0 to 3, 0. Now, I made a remark a couple of minutes ago about zoom trig. Now, zoom trig allows the user to select a new viewing window that has an appropriate dimension for viewing trig functions. And this is a very useful zoom feature when you're graphing trig functions, but also when you're graphing parametric equations that are trig functions as well. So what we would do there is press menu, number 4 for window zoom, and then number 8 for zoom trig. And what you'll see there is that the scale tick marks are now worth 0.5, which is fine. Notice now that on the horizontal axis, the endpoints for the viewing window are -2 pi to 2 pi. And in perspective, the endpoints for the vertical axis are -4.19 to 4.19. What that's doing is it's ensuring as well that you get the correct and best shown, best displayed ellipse, rather than being misled if we had a different window saying, oh, maybe it's a circle. Well, it's not a circle, it's an ellipse. So it's really important to have zoom trig as part of your arsenal, and also to set really good windows, particularly so that you can discern between a circle and an ellipse. Okay. A couple of extra features here. So again, what you see here, this is the Cartesian equation that's being graphed. Now, this is being graphed in a different graphing mode. Notice that I've still kept those zoom trig settings, but I'll show you how this one was graphed. So if I press menu, and then go to graph entry edit, and then go to equation templates, and then number 4 for ellipse. Number 1 is center form. And if I go, and so what you see there, here you get your template. So what I did was I put in 1 there and 2 there and 0 there and 3 there. As you can see, when I hit the navigation pad up, so there's a nice template for you. So x minus 1 all squared on 2 squared plus y squared on 3 squared equals 1. Okay, so that's one way of plotting that ellipse. Press escape and go to the next page. I'll show you another way. Here I'm again going to press menu, then 3 for graph entry edit, and then this time number 2 for relation. And we can also enter in relation graphing mode. We can enter the equation for the ellipse in this form: x minus 1 all squared on 4 plus y squared on 9 equals 1. And so again, we get a very nice representation for that ellipse. And finally, this is a feature that is worthwhile exploring. If you press menu and then number 6 for analyze graph, down the bottom there, number 8, you've got an analyze conics set of commands. And this takes us back to the old days of pure mathematics and the coordinate geometry that we used to study. And so by clicking on the graph, analyze conics will confirm or give to you particular features of the plot. Now, the one of interest to us, well, we could do the foci. So if I went for number 3 and then just made contact with the graph, you can see there's your 2 foci. Press escape, menu, and then analyze graph. Number 8, analyze conics. The one we're interested in is center, so we press 1 or enter, and then we make contact with the, we make contact with the graph there and press enter, and you'll see that what's anchored now on the screen is the center of the ellipse with its coordinates 1, 0. And so that's not a very well-known feature, but I think it's a very, very useful feature of the analyze graph suite of commands. Okay, I think that's all I wanted to talk about for that example. So moving right along, this one's quite straightforward, and the previous example, we focused a lot more on some learning mathematics and doing mathematics. This one is essentially a doing mathematics example. So we've got 2 intersecting lines and where they meet, and we want to find the position vector of the point of intersection of those 2 lines that are specified there. This part of the line, that's a point on the line, or represents a point on the line, or a position vector. And this vector here is the direction vector, and T and S are real parameters, and that's our general form for a vector equation of a line. Okay, so we want to find where these 2 lines meet. And here is a calculator page, and I should give you some brief remarks about what I've done here. We go back to the previous page. I've got a position vector R1 of t and another position vector R2 of t. I haven't used the define command here. I've used the assign command, which works the same way. Assign is colon equals, and the way to access the assign command is you would press Control and then the symbols template. If you have a look above the symbols template, there's in red there's a small colon equals. So I'm going to assign R1 to be that vector equation of the line, and R2 of S has been assigned, and it's assigned to be that vector equation of that line. And what we also need to give you some guidance about is Normally, what I would do is I would represent these vectors. They're represented here as row vectors for purposes of saving real estate. The idea is really they should be, although mathematically this is fine, they should be expressed as column vectors, but what happens there is they take up too much space. So that's why they're specified as row vectors. And just to show you how you would access that template so that you can get that 1 by 3, if you like, row vector, 1 row and 3 columns. What you would do is you would press menu and then press escape, because I've got a better way. What you would do is you would press the catalog button, and that's the one with the open book icon, and it takes you to the M by N matrix template. Here you've got a 2 by 2. That's a 1 by 2, 2 by 1, but this is the M by N. So this is the one we use so that we can set the dimensions or the order of the matrix. So with that highlighted, you press enter. The number of rows, we want that to be 1. So we press down arrow to 1. We're happy with the number of columns being 3. So we press tab through to OK and press enter. And that shows you how I was able to get access to that template. And then it's just a matter of, in this instance, typing in 2, -2 and 5 respectively. So I'll press delete and backspace there. So I've assigned the two, they're the two vector equations of both those lines. And what I've done here is I've equated the I and J components to form 2 equations in 2 unknowns, T and S, and solve to find the value for the parameter T and the value for the parameter S. And then that will, when we substitute those into our vector equation of a line, then we will determine the position vector where those 2 lines meet. So you can see here, we've got this command called linsolve. Now, how did we find that? Press menu, 3 for algebra, and then number 2 for solve system of linear equations. There are 2 equations here, but we could set the number of equations to be more than that. We press tab, and rather than x, y, we're changing it to t, s, because they're our 2 parameters that we're interested in solving for. Then press tab through to OK, and then press enter. And there's our template all nicely set up for us. And then all you need to do is enter 2 plus t equals 2 plus 2s, and -2 minus t equals 4 plus s. Of course, the mathematics here in solving these system of equations is very straightforward. I mean, if you just added the 2 equations, you can quickly see that 0 equals 6 plus 3s, and therefore s equals -2, and substitute s equals -2 into either of those equations, and you find that t equals -4. So that's, you know, it's quite straightforward in terms of by hand considerations. With our values obtained there, there's be very careful there. In that list, t corresponds to the -4 and s corresponds to that -2. So pay attention to that. And with R1 of t and R2 of t assigned, then all you need to do is just enter R1 of -4 and R2 of -2. And so what we've found is that the position vector where these 2 lines meet is -2, 2, 1. And notice that we're working again with row vectors. What you would get the students to do is express them as column vectors using the specified notation that the examiners want you to use for your Queensland exams. What I've also shown here this is two equations. This is equating, again, the I components and the K components and solving. And you get the same value for T and the same value for S. Okay, moving right along to our third example. We're going to bring the notes pages into far greater focus here. So the area of a triangle, so vectors, or in particular the cross product, can be used to determine the area of a shape such as a triangle. So our example here are snips again from the Queensland TRB using the Microsoft word snipping tool. Find the area of the triangle ABC with vertices given by those coordinates. Now we know that, well, let's first of all define A to be the area of the triangle, where A is equal to 1/2 times the modulus of vector AB cross vector AC, and where vector AB is vector B minus vector A, and vector AC is vector C minus vector A. Okay, go to the next page. And we're not going to do these calculations on a calculator application. We're going to do it on a notes page or a notes application. So we've seen so far that you can write some text, but look, this is a far more exciting notes page. We've got some objects here that it appears as though we're doing some mathematics, and it looks as though, if we scroll down, it looks as though that we're able to work out the area of this triangle using these really wonderful objects called math boxes. So let's show you how you enter a math box into a notes page. There's two ways. Now I've just found some space here. This is like my working space. I possibly will end up deleting this, and this will end up being our first line again in a moment. So one way is to press menu, number 3 for insert, and 1 or enter is maths box. And notice next to maths box, you've got a control plus M. So the shortcut for inserting a maths box is control M. So if I press 1 or enter, here's a math box. Now I'm out of the math box now. I know that I'm in one. If I go one to the left, math boxes have a dashed border, and you know you're in one when there's like a dotted outside border, if that makes sense. So there, I'm not in a maths box, but if I started typing in there, I'm inside a math box. Okay, so I might just get rid of that. Actually, no, I won't for a moment. I'll just leave that there and just show you what we can do is we can say, well, okay, we can assign vector A. So that's typing in A, and the assign command is control symbols template. We can assign it to be the row vector. And again, I'm using row vectors for the purpose of real estate as 1, 2, 5, which corresponds to the coordinates there of vertex A. So in a sense, vector A is position vector OA. It's relative to the origin, if that makes sense. And so how would you get the row vector template? Well, it's a little bit, well, it's actually the same here. If we go to the catalogue and then the M by N matrix, and you would repeat what we just did before. So press enter, and then reduce that to 1, number of columns 3, tab through to OK, and then press enter. So that's how you would access that. So I'm going to get rid of that space now. So what you do is you input vector A. The input is in blue and the output is in green. And so, and math boxes, you can alter the appearance of them. So I'm going to go inside this math box. I'm going to press menu, then number 5, math box options. Number 1 or enter is math box attributes. And we can change the appearance here. So, and for notes pages of this ilk, my advice is to show the input and the output. But you can also do things like hide input, hide output, no calculation. Press escape. The insert symbol, I'll show you a little bit. Some of my math boxes later have the equal sign, and that's where I got that from. Press escape. You can set the display digits. You can set the angle. So you can have localized settings set up within a math box. Right, so press escape. So what I've done here is I've in a maths box, I have assigned vector A to be that. I've assigned vector B to be that. I've assigned vector C to be that. Okay, so that's vector OA, OB, OC. Then what we need to do is we need to work out what vector B minus A is and what vector C minus A is. Now, what's lovely about this is that these math boxes are all interactive. So, for example, if I go in there, and I'll need to remember what I changed this to. If I change that entry from, or element from 0 to 1, and then press enter, right, watch what happens to C minus A. Go back to 0. What happens is you get an automatic update. So these math boxes, they're linked and they're interactive, and that's very, very powerful. They're two very powerful qualities of a math box. And so what we've got now, got a situation where we've got to build the formula. And from our previous page, in mathematics, the area is half times the modulus of vector B minus A cross C minus A, or in other words, half times the modulus of vector AB cross vector AC. So we've got a couple of commands here. So this looks slightly complicated, but it's quite straightforward. So in that math box there, use the fraction template and we enter a half multiplied by. Now, the modulus of a vector is given by a command in TI-Nspire called the norm. So how do you find commands in the notes application? It's different to the calculator application at the start, but then it becomes the same. So if I press menu and I go to number 6 calculations, what you'll see now is a familiar set of commands which you also have access to in the calculator application, from define variables all the way down to finance. Number 7 is matrix and vector. Number 7 is norms. So that's where you find norm from, and press escape. I'll press escape so that we can see the screen. This is an example of a nested command. So first of all, the norm, and now we want the cross product. So we work out the cross product. It goes inside out, if you like. We work out the cross product, and then we work out the magnitude of that vector. That's how that's working. So to obtain the cross product command, what we would do is press menu, calculations, then matrix and vector, and then we've got to scroll either up or down. We might scroll up, might be better, to vector, and then arrow across. And from our vector set of commands, you can see there cross product number 2. All right, so you would then paste that into the entry line. Okay, so that's how we've devised that. And when you enter that and press enter, you get the exact area of root 478 on 2. I've got a similar math box underneath, except this time I've changed 1/2 to 0.5. And what happens is if part of the input is a floating point decimal, then the output is mandated to be a floating point decimal. So it's nice to have the exact value and also the approximate value there as well. You can use a command in here called approximate as well, but there's no real need. We've got the exact value and we've got the floating point decimal value there. Okay. Now, what I did before this webinar was I took this page and I made a new TI-Nspire document called the area of a triangle. Okay, so here we've got an area of a triangle. It's one page. And what we can do is we can form what's called a widget. All right, so a widget is a one page, usually a notes application. You can also add applications in split screen formats and split page formats as well. But it's essentially, for the beginner, let's just say that it's a notes application. And what you can do is you can save the widget and then call it up again if you want to do a similar calculation. So let's see how this works. So what I'm going to do now is I'm going to go to Doc, 1 or Enter for File, 5 or Enter for Save As. And what you can do is you go into your folders and you find My Widgets. In My Widgets, the file name is Area of a Triangle. So I press Tab and then Save. Document with the same name already exists, overwrite it. So I'll say yes. Okay. Let's come back to our Unit 3 vectors document. And we'll just go to another part of this document. So we're in another problem. And we say to ourselves, oh, okay, I might want to use that widget to work out the area of a triangle. What you can do now is you can press Doc and go to number 4 for Insert, and then A for Widget, and all your widgets are listed here. If you've never produced a widget before, there might only be one in there, like stopwatch, for example, might be the one that's in there. I want to call up area of a triangle, so I'll add that. Notice that it's that page. All the inputs are there, but none of the outputs. But what you can do is you can highlight all these math boxes, then press Menu, Actions, Evaluate, 1 or Enter, and there they all are again. So you can change these. So let's say B, for example, is 3, 4, 1. Press Enter. Notice that we get a new vector B minus A and a new area. Change that to 4, for example, and it automatically updates. And so I think the widgets and the notes application is extremely powerful, so that you can have them saved on your device and you can call them up at any time to perform, a quick calculation. There's no doubt that students will be calculating quite a few areas of triangles throughout their studies using the cross product, and that's a very quick and convenient way of doing that. Okay, so I'm going to control navigation page up because I want to delete that page now. On to our next example, paths of two particles. So two particles meet when they share the same position at the same time. I just mentioned quickly before I do that is that here is the snipping tool on the notes page, and this shows us the calculation that we just performed on the notes page there. So my apologies for forgetting that, but that corresponds to the calculation that we did for the area of the triangle. Okay, back to this one. Two particles meet when they share the same position at the same time. The motion of two particles are given by those two position vectors. Find when the two particles meet and determine the coordinates of their meeting points. So the criteria here for particles meeting is that they share the same position at the same time. Okay. Now, I've given you some good guidance already as to the graphing here. So I'm not going to go into the mechanics of the graphing, but I've used the parametric graphing mode. So this is particle 1. So x1 is 2t minus 3, and x2 is, y1 of t is t squared plus 10, and x2 of t is t plus 2, and y2 of t is 7t. Okay, so, and we've got these set up beautifully. Now, their paths cross, no doubt about that, but do they actually meet or collide? And the best way to, besides algebra, to see this, and it's really good to do this before doing the algebra, is to perform an animation. So we press menu and then 5 for trace, 4 for path, and then we just want to check path setup. So we want parametric. Now I have set this up prior. Path step of 0.1 in this instance is really good. You can be given a good clue as to what the path step should be by doing some mathematics before the start of the class, just to determine, well, okay, if I use a particular path step, then I know that I'm going to see the point of collision, or the point where the particles meet. Okay, so I've chosen 0.1, tab through to OK, and then press enter, and then menu, trace, and then path plot, and then parametric. Okay, so we've got our initial starting points for our two particles. So particle 1 starts at -310, particle 2 starts at 20, and it's just a matter now of the t value is going to change by 0.1. So we're going to press the, start the animation, we press the play button, and we can see there the animation going in increments of 0.1. Right. Now I wanted to stop at t equals 2. That's a very interesting situation here. At t equals 2, the particles share the same y coordinate, but they have a different x coordinate. So they have not met. Okay, you can tell they have not met. Continue the animation. All right, so continuing on in increments of 0.1. They are getting close to each other. Getting very close. There we go. They collide or meet at t equals 5. They share the same coordinate, 735, at the same time. All right, so we have dynamically or visually shown that the particles meet. Determine the coordinates of their meeting point. Well, we've actually done that as well. So in a sense, we've answered the question without performing any algebra, which is quite powerful. Press escape there, go to the next page, and what this does is ratifies what we saw on the graphs page. I've assigned R1 of t. Now I can use X1 of t and Y1 of t here because we're in the same problem. So X1 of t, Y1 of t, X2 of t, and Y2 of t, they are recognized. All right, so that's quite a useful feature. It shows how we can link applications within the same problem. So the graphs and the calculator applications are working nicely together in synergy. I've used the numerical solve command to solve X1 of t equals X2 of t, and so they share the same x coordinate at t equals 5. Without using a condition, I've used the numerical solve command, and as a reminder, that's menu, algebra, numerical solve, 1 or enter. When we equate the y components, if you like, we get t equals 2, and that was the point that I showed you in the animation where they shared the same y coordinate but different x coordinates. And if you add a condition, so we want to look at the equating the y components and solving for t, given that t is greater than 2, we see there that t equals 5. So you want to see, so in terms of the x coordinates, it's x equals 5, and for the y coordinates, it's y equals 2, y equals 5, and the t value that's common to both is 5, t equals 5. Okay. And just continuing on there, Again, I've got R1 of T and R2 of T. They've been assigned. And in the calculator application, we can also determine these. They're the point, that's the point of collision, R1 of 5 and R2 of 5 at 735, and that's represented there as a row vector, and 114, 414. That's the situation when T equals 2. Okay. Our final example is the vector calculus, quite a straightforward one. But a position vector as a function of time moving in a plane is given by that position vector. You should be able to glean from this quite quickly that this path is going to be a parabolic, and we want to find the initial position of the particle, the initial velocity, find when the particle is moving parallel to unit vector I, and find the particle speed at t equals 1, giving our answer correct to 1 decimal place. Okay, so again, this is from the Queensland TRB and Microsoft Word snipping tool. We've snipped the image from the book into the notes application. So what have we got here? We've got a calculator page, and what I've done here is I've assigned R of T, so assign is control symbols template, as a 1/2 row vector. So if I press the catalog button, I've used that template there. Scrolling back up. So R of T is 60Ti plus 20 plus 45T minus 5T squared J. What I've done here is this is a reminder of what part A is, and this is a comment. Now, to add a comment to a calculator application, press menu, actions, number 6 for insert comment. And this is a prompter. It's saying, well, okay, I've got to find the initial position. So the initial position, we should be able to readily note that the initial position is going to be 0, 20 or 20J, if you like, by substituting T equals 0 into there. So R is 0. Find the initial velocity. This is finding, if you like, V of 0 or R dashed of 0. So we know that R dashed of T, or the velocity, is going to be 60 I plus 45 minus 10T J. So what we've done there is we've pressed menu and then number 4 for calculus, and then number 1 or enter for numerical derivative at a point, chosen the variable T, press tab for the value 0. We want the first derivative, and then tab to OK and press enter. And there already is the template. So all I need to enter there is R of T. And that's how we get 60. The initial velocity is 60I plus 45J. We've inserted a comment for part C. Find when the particle is moving parallel to unit vector I. What you can do there is that's when that's the case, the J component is of velocity. The J component of velocity is 0. All right, so we solve 45 minus 10T equals 0 for T, and we get T equals 4.5. And part D is find the speed at T equals 1 and give your answer correct to 1 decimal place. This is, again, another instance of a nested command. And so coming down to a new entry line. To find norm, you would press menu, 7 for matrix and vector, 7 for norms, 1 or enter for norm. And then, well, it could be a bit crafty here. We could go up and grab this and then change T equals 0 to T equals 1. And that input looks like that input there. Press enter, and that gives us the exact speed at T equals 1. We want it correct to 1 decimal place. So if we said, well, okay, let's press Control Enter. That gives us a floating point decimal answer. If we want that rounded to 1 decimal place, I know it's quite straightforward. that it's 69.5. But what you can do is from menu, number 2 for number 8 for number tools, and then number 1 or enter for round, we can round that to 1 decimal place. So the syntax there is comma 1. Press enter and we get 69.5 there. Okay, very close to the end. We can also produce a plot of the position of the parametric equations which govern the position vector as a function of time, and that gives us the Cartesian equation of the path. We can see that it's parabolic there. You can see that it's the particle starts there at 0, 20, and that we would have found there that's going to be very close to t equals 4.5 when the particle's moving parallel to a unit vector I. Now, if I press Control T, we get a split screen, which is really nice. And on the left, we have the plot. On the right, we have a tabular representation. To move between applications on the same screen, you press Control Tab. So now the graph application is ignited or alive. Control Tab. Now the table representation is active. I press menu 1 or enter for actions. You can resize the column widths if you wanted to. Press escape, go down to number 2, press enter. You can remove the table, you can delete a column, you can edit the table settings, or you can edit the expression. So what I'll do is I'll remove the table. Going to the next page, here is an example of the table, and we've got t, x1 of t, y1 of t. I've set up the table settings to be in increments of 0.3, and so if we come down to 4.5, that was where the particle was moving parallel to unit vector I. The coordinates of that point were 270, 121.25. And we could see that if we went to here and we did a trace, and we went to trace, and we went to trace step, 0.3 looks good. And then menu, trace, graph trace, and now we use our arrow key. We can move this to give it a bit more room. We can see there that the coordinates of that point at t equals 4.5 is 270, 121.25. Okay, so that takes us to the end of this webinar. So thanks very much for your attention for that 55 or slightly longer minute presentation. Hope we got something out of it. Try to show you a few extra tricks, a few extra what's going on behind or underneath the bonnet there, and hopefully you can take some of these tricks into producing Nspire files yourself that you can take into the classroom and use. So without further ado, I'll hand you back to John, and thank you very much for your attention.
Handing me back to Geelong, I don't mind that either, Peter. I can see which football team that you support, mate.
Yeah, apologies for that slip of the tongue.
All right. So Peter, thanks very much for that. And I think that the way that you use the math boxes and not only use those but then converted them to a widget is really powerful. The nice features of the trace with the path plot and then the path settings, I think that's a really nice feature as well. So thanks for doing that. Peter, just keep an eye on the chat. Is there anything else that you would like to add just before we start wrapping up?
No, nothing for me to add other than, again, my thanks to to the attendees and anybody who watches this subsequent. And thank you, John, for your expert stewardship.
So just a reminder that our dedicated Queensland TI education page can be found at education.ti.com/Oz/Queensland. And if you scroll to the bottom of the page, you will find the downloadable teacher resource ebooks, like what Peter was using or talks about today at least. And a lot of those is also shared on there. We're beginning to wrap things up, as I said. So if you have any last minute questions, please try and get those asked, as I know Peter will endeavour to answer them, or equally add them to future webinars and planning. And when you leave tonight, a brief form question survey will automatically appear in the browser. Your feedback guides us as we plan future online events. We will listen to your feedback, and so we hope you will share your thoughts in a post-webinar survey. And if you're watching live, in the next 24 hours, you'll be emailed a link to the past PD events. I also encourage you all to check out our student, or teacher for that matter, online courses and our very own TI dedicated YouTube channel. And well, that brings us to the end of our webinar. Peter, thank you once again for everything you've shared with us. I really appreciate it, and I know that our viewers have too. So thank you, Peter.
Thanks very much, John, and thanks all.
And thank you everyone for joining us tonight. We hope that we enjoyed it, and we look forward to seeing you back online soon. Thank you very much, and have a good evening.